All right, I guess we should get going. Mic is on. Cool. Welcome, everybody. It's great to have such a huge crowd. So my name is Robert Hodges, and I'll be doing this talk today called Fast, Faster, and Fastest. And I'll be looking at object storage, cloud block storage, and NVMe SSD in analytic databases. So I want to be clear here, Laszlo, who also his name is up here, he actually lives in Hungary, and he and I have been collaborating on this talk, and he actually did a version of it for Kubernetes Community Days a few days ago. So he is not here today, and my name is not Laszlo. So I'm going to make just some quick introductions. So once again, my name is Robert. I'm a database geek. I've been working on databases actually for 40 years. I've been writing code since 1972. It's been a while. And I worked with a variety of different database systems. I spent about 10 years working in the MySQL community on things like replication and clustering. And my current day job is I run Altinity, and we're a service provider for ClickHouse. Has anybody here heard of ClickHouse? Okay, great. You're going to learn a little bit more about it because we're going to use it as a case study. So ClickHouse, it's a really great analytic database. So we have a cloud for ClickHouse, so people can run it in our cloud, or they can do regular enterprise support, or they can just point us to a Kubernetes cluster and we can manage it for them there, but they get to hold on to the data and all the open source software that's running on it. So we wrote the Altinity Kubernetes operator for ClickHouse. We're really big on cloud native. It's pretty dominant in enterprises now. And so some of the talk goes into that. Laszlo, who's not here, he's a UI engineer and also was interested in this topic. All right, so what are we going to look at? So this talk is really, because we have this cloud, which we've been running for 2.5 years, we spent a lot of time thinking about what are the main forms of cloud storage and how do they work? How do we measure their performance? How well do they work for analytics? So just looking at the first part of the talk is just explaining how these storage types work in the cloud, and then put an analytic database on top, and then do some measurements to find out how storage affects the analytic database performance. And I want to say that this is how many of you have done performance testing? I know, Sveta, I know you have, but performance testing is full of surprises. And there is no absolute answer. In fact, if there's one lesson from any talk on performance, is nobody has the answer. And so it's not the destination, it's the journey and the things you learn along. And so this talk will definitely focus on that. So let's have a look at cloud storage. First of all, how many people are running things in a cloud like Amazon or GCP? Okay. All right, so for the others, you guys, so some of this might be more educational. So there's 3 different types we're going to look at, and what I want to do is for each one of them delve down and say how do they work, just in general. And so we'll start with NVMe SSD. So this is flash storage attached to, for example, PCIe bus, and it's these little Kingston cards somewhere down there. This was actually an incredibly hard picture to draw because we have no idea what the heck is going on down there in Amazon. But what we do know is that if you get a VM that has access to NVMe SSD, it's some kind of physical host. It has NVMe SSD attached, so presumably there's a PCI Express bus down there. And then we have VMs riding on top of that, and then we get some guarantees from Amazon about what those, what portion of that storage that they're going to get. So the storage, once again, is locally attached. And then the way Amazon does it, and my examples today, by the way, will all be from Amazon, although other clouds have similarities, is that Amazon says that, as it puts the VMs on the host, it gives each of them a fraction of the I/O bandwidth. And the way that it's done is that if you hire out like an i3 2X large VM that has, I think, 8 vCPUs, that is going to get, say, X amount of bandwidth. If you go to a 4X large, which has actually 4 times the number of, that would be 2 times the number of CPUs, you're going to double the bandwidth. So basically, the number of vCPUs you have is a proxy for how much bandwidth you get. And we can actually measure this and prove that it at least works in the case that I tested. All right. So how do we measure it? Well, there's a bunch of really great programs to test disk performance. So of course I wrote my own. And it's called IOPerf. It's a really bad name. It's going to change. Somebody else already did it. But the reason I wrote one for this talk was that I wanted to be able to do apples-to-apples comparisons of block storage and object storage. And the tools that I had access to don't do that. So I wanted something that would make them comparable. So this does, how many people have used Sysbench here? Okay, it's a great program, really awesome. I've used it a lot. So these programs all do about the same thing. You can write to the disk and you can tell it what you're going to do. This is saying, hey, write to the disk, do 512 megs of data, so half a gig. How many threads, how many times you want to iterate through, how many files you want to have. That says write all 50 files once. Do fsync at the end of each write, so on and so forth. And then you can read them back. And here we have the 50 files, 4 threads. And we're going to read them 500 times, because that's going to allow us to see some nice caching effects. This is a test I'm going to run on each of the types of storage. And then we'll see what we get. So what I did was pulled up an i3 VM, i3 4x large, and just ran this test. And here's what it looks like. So here's how to read these graphs. They're throughput, but in a little bit different way from the way they're sometimes presented. So what this shows on the y-axis is the duration of your writes. Like each of those writes we're doing, you're going to see the duration in milliseconds. So what that means is if you point to this dot right here, that took 2,000 milliseconds or 2 seconds to complete. The horizontal axis, the x-axis, is how long, when did it complete? So what you're basically seeing is each of those dots represents the completion of the write, showing how long that one write took and how long it was down the path. And what's interesting on NVMe SSD is if you're f-syncing at the end of these writes, forcing this, basically sending a command to force it to the device, you actually get fairly unstable performance of individual writes. This is basically overloaded. So what I can see is that I actually went back and tested it with a single thread, and you get a nice straight line. But if you have 4 threads f-syncing this stuff, you get this kind of scattered pattern. But basically what it's saying is, to write a half gig, on average, these writes are completing in about 2.5 seconds. On the read side, you can see that we go ahead and do our 500 reads, and what I do is I flush the caches. I flush the operating system page cache. So what that means is when we read the files the first time, they're going to actually have to go to the device and get the blocks there. And so that's really slow. And so that's why you see these first 50, there's 50 reads up here, which are taking a little over a second each to read their half gig of data. And they're going kind of slowly. And then you see, after the 50 are done, at that point, the operating system has read these files and it's pulled the blocks into the page cache. So it's cached in memory. And then all of a sudden, you start seeing the reads drop down and they go faster and sort of in aggregate much quicker. So this is classic sort of page caching effect. Slow to begin with. Once the caches are loaded, it zips right along. Any questions about that? This is pretty standard stuff. Everybody knows what the page cache is? Okay, we're going to be talking a lot about caches because they're a big deal. So another thing I did was just test out this proposition that there actually is a difference in the bandwidth of between different VM types. So what I did was ran this same test, and I used an i3x large, which is about 1/4 the capacity of a 4x large. And in the Amazon docs, and let me explain, this graph is showing something slightly different. It's just showing the percentiles for the writes. So what this is saying, at the 50th percentile, that is the median write performance, was about 3 seconds. And then the red line, which is the smaller VM, the median write performance was about, as we can see, 6 seconds. So what you see is a pretty clear pattern for all percentiles that the smaller VM takes about double the time. And what's interesting, and when I first saw this, I thought, wow, that's not what Amazon said. But it turns out that when you're using Amazon devices for NVMe SSD, they give you, sort of an SLA for performance, but it's across all attached devices. And it turns out that this little VM just has one attached device. The big VM actually has two, and I'm writing to one of them, so I get double the performance. But this is kind of cool because it shows that the performance is pretty much as Amazon advertised, at least the ratio between them. It might not be the throughput we expect. All right, block storage. So block storage is really cool. It's like hiring. How many people run databases on SANs, storage area networks? Okay. Used to be a thing, less so. But if you use elastic block storage in Amazon or similar features in other clouds, basically what it is it is a separate network that connects to your host. So that's the storage area network. And so you don't contend with, like, your applications are not fighting for bandwidth on this network. And then you have just a service that just has a huge pile of storage, and you can carve out pieces of it, and they then get mounted on your VMs. And so, you'll have in this case, an M6i 4X large. That's the VM type I picked. And then it mounts like a nice big fat EBS volume on it that we can test. So it's the same, from the operating system point of view, you can't tell the difference. The storage is coming across the network. So that raises the question, well, what does the performance look like? So when we do this same test where we're just blasting these writes out, the performance is actually pretty close to NVMe SSD. And I found that super interesting because, the word on the street is, hey, if you want speed, use NVMe SSD. Well, it ain't so. The EBS, which sometimes is criticized for being really slow, actually is quite fast, particularly if you're on a VM that's large enough to get decent network bandwidth. The interesting place where, at least in these tests, that there's a big difference is the cold reads from storage are slow. For these, they're taking about over 3 seconds to read those half gig files. Moreover, that's slower than it took to write them. And Amazon doesn't really talk about how EBS works inside very much because they don't want people to depend on it. But that's kind of interesting that the writes are fast and the reads are slower. I don't know why that is, and it's something to look at later on. Once they get through once they get through reading them, then the blocks are all in the page cache, and you get that blue line where it's just jamming through and reading these files now in about 1/4 of a second each. So EBS is actually pretty good, and you don't necessarily have to. And one of the big advantages of EBS is you can, and the reason we like it, we use it in our cloud, because if you want to change your VM size to apply more compute to a patch of storage, for queries, you can just respin the VM, reattach the EBS volumes, and then you've got that much more computing power. So it's a really handy storage type. So the last one is object storage. So and object storage is, how many people have used object storage? Okay, it's brilliant. It's I think one of the most innovative things that Amazon ever did, even though it sure didn't look like it at the beginning. They had 3 services, which I think were the SQS, EC2, and S3. And when it came out, it was not obvious what this thing was good for. Well, it turns out it's good for a lot. So basically, the way it works, as most of you know, you have buckets, and they have a URL, and then you can have a collection of files, and you just put them out there, and you get them back. So basically, put and get operations. And so a couple things that are really important about this from a performance perspective. One is these puts and gets. These are just network calls from your application. So when you think, and so in performance, you want to think about who's sharing stuff that I'm using. You're on the network and you're using the same connection that your applications are using, maybe to ingest data or to do other things than talk to storage. So you're competing there. The other thing is, because it's just an application call, this OS page cache has no role here. It's simply not used. So that means you don't get caching effects. And in fact, unless you build them yourself. So in fact, here's what happens when we run that apples to apples testing. It's, here we see that actually EBS writes, which are often said to be kind of slow, are actually way faster than object storage, which has very consistent performance. It's kind of interesting. And this is partly because there's no equivalent of fsync here to slow things down. Maybe that's why it's, I presume it's doing something good when I push the file up. But, and then the reads, again, very consistent in these runs. They weren't being interfered with. It didn't have applications interfering, but they're way slower than those reads that go into cache. So the last graph is just showing a comparison of reads across these different storage types, allowing it to use the, starting cold and then filling the cache. And this shows the distribution of the reads, the percentiles. And what we see is that there's this, for the block storage types, like the blue is NVMe SSD. For EBS, they have very high, P90 and P95, P99, because those are the files that they're still reading out of the buffer cache, or excuse me, from cold from storage. And then once everything's in cache, of course, the reads are really fast. No difference up to about 80th, or actually really about 90th percentile. Object storage has a little bit of variation, but again, it's pretty consistent, but just slower. In fact, much slower in this example than reading from the page cache. So that's our tour of storage. Any questions on that? Because we're now going to put a database on top of it. You ready for it? Okay, let's do it. Databases are great. All right, so we're not going to do MySQL, though. We're not going to do Postgres. We're going to do an analytic database. And so we're going to use ClickHouse because it's the thing I work with every day, and it's something I actually know something about. An analytic database is, unlike MySQL, Postgres, Mongo, are designed to read very large amounts of data, to read it quickly, and to have stable latency. So for example, ClickHouse, you can see the different properties of it. It's kind of like, it has a lot of similarities to MySQL, but it does analytics. So it has column storage with high compression, very high levels of parallelization for queries, and scaling. And the kinds of problems that we see people solving with this are things like security event and incident management. Like your typical security monitoring system, like Netscope or something like that. And what they do is they want to identify something that happens really quickly. So you want to have quick response, and then you want to be able to look through historical data, often going back weeks, months, or even years, to figure out where this incident emerged. So you need to have very high performance on that as well. This database solves that problem quite well. So we like Kubernetes, and we use it for our cloud. It's also becoming increasingly common in enterprise environments, just as a common platform that I can deploy my application, for example, on Kubernetes running on my laptop. I can put it in, like Kubernetes running in a data center. I can put it in Kubernetes on Amazon. I can put it in Kubernetes on GCP, so on and so forth. It gives the applications portability. So our cloud, we made that choice because we wanted the cloud to be able to run anywhere. And in Kubernetes, if you are not familiar with it, what Kubernetes does is it's just a management system for applications that are based on containers. In other words, Docker for most people. So you would have a ClickHouse server talking to storage. This is just like any database talking to a patch of storage. And in Kubernetes, you define a couple resources. You would have a stateful set. That's a resource that has a consistent name and knows that it has storage attached to it. And then you have a pod. and a pod is a running container. It could be multiple containers, actually. So you can think of it as a process. And then storage, you have a claim, which says, hey, I want, like 1,000 gigs of storage, and I want it on GCP, GP3 EBS volume, or EBS, and then the persistent volume fulfills that. And so it maps to EBS storage. So what it does is, it has a lot of infrastructure to define your application. This seems like colossal overhead if, you're building just running MySQL talking to a single file system. If you're talking a distributed system like what we run, where you have 2, 4, 6, 8 nodes or, up to dozens, it turns out to be extremely efficient and allows you to define the whole application. The thing that sets it up is something called an operator. Anybody here worked with operators? Like Percona has an operator. Yes. What are you running?
I've only messed around with it personally, but we use operators. We were testing out the Altinity ClickHouse.
Yay. Okay. Yeah. So we've been working. Did you start on GitHub?
I'm sorry?
Did you put a star on it on GitHub? That's an important step in testing it out. We're trying to get the stars as high as possible in the project. So I'm just kidding. So what that does is, so Kubernetes has these built-in resources like the ones I just showed on the previous page. Operators, one of the reasons they're so popular is they allow you to make more resources. So we have the operator allows us to create a resource definition where with a piece of YAML about this long, we can create a full-scale data warehouse cluster with as many as like dozens of nodes if we want to. And what you do is you feed it into Kubernetes. It says, hey, this is a ClickHouse installation type resource. It hands it off to our operator because it knows that our operator is supposed to do that. It then defines the resources out on Kubernetes, and Kubernetes makes the infrastructure obey. And so that's how the database gets set up. So what you get is, like if you have a simple case, you get that pod, and that's going to map to a container running in this case, an i3 4x large VM. So there's, on the Linux operating system, there's a Docker container going to be running here. And then there's a patch of storage that you're getting access to down on your NVMe SSD. Same thing over here, when we're using EBS, we're going to, have a container running in our VM, and then we're going to have a patch of storage somewhere out in EBS to talk to. However, there's an important caveat. So containers really change databases in subtle and not so subtle ways. A really big thing that you run into very quickly with container-based systems is they don't own the page cache. And as you're going to see in a few minutes, well, if you've already seen, the page cache is really critical to file system performance. So the fact that you don't own it, what I mean by own it is like I'm in the Docker container, I can't clear the cache, for example. Also, if there's a bunch of containers, maybe I'm not the only container running on this VM. Other containers are also depending on that page cache. So if I'm running a database, I need to be very careful that I'm not contending for this really precious resource that affects performance. So we have to actually adapt things a little bit even to test in this situation. So what I did was I ran a program called ClickBench, which was originally written by Alexei Milovidov. He's the designer of ClickHouse, the lead committer, and it's actually it's a nice benchmark. It has about 15 gigs of compressed, about 60 gigs uncompressed e-commerce data, sort of web hits on an e-commerce site. So it's 100 million rows. It has realistic queries. It's a single table, and it's pretty easy to set up and run. So basically script-based. Now, normally what it depends on is being able to do things like clear the buffer cache, but if we're out in a container, we can't do that. So I did some slight adaptations. I did a version, just did a command that is going to force direct I/O. So in other words, skip the cache. ClickHouse can do this. And then in the second run, we just allow it to do whatever it wants. So it'll use the page cache. But basically the same runs. So here's what happens when we run this benchmark. So 43 queries doing all kinds of different things. You'll see and we run the test results in NVMe SSD. And here's the big surprise. It doesn't matter whether, because we're only testing reads here, by the way, because that's the thing we really care about. But the thing we see here is there's no difference between going straight to the storage versus using the page cache. So you can see these are lines. This is the performance. There's only one single case where there was any difference, any perceptible difference at all. So the page cache just didn't matter here. We'll get into why that is in a bit. So that's an interesting result. So why isn't there a visible difference? That's kind of interesting, because it is so much more expensive to read from the device, from the page. And the basic answer is that ClickHouse is designed not to make this be very costly. So ClickHouse minimizes I/O by compressing it, and I'll show an example in it that really goes into how much it saves you. The other thing ClickHouse does is it reads in parallel. So we had not one thread, but we had 8 threads processing that query and doing a parallel scan. And so as a result, I/O is just really, really cheap, or a really small component. And in fact, the query results you're seeing there are dominated by compute. They're really dependent on how much CPU you can apply to them. And we'll see a concrete example of that also. So here's another one, test results for ClickHouse on EBS. I just want to check, I have 10 more minutes. Is it 20? Okay, cool. Then we'll get through this and have time for questions. So same test on EBS, another surprise, EBS, which many people have said is slow as a dog. Again, it actually isn't. For the most part, we see this one query. This is query 24. That's a select star on about 80 columns. Yeah, it's slow, and yes, there's definitely a difference, but virtually every other one is the same. So, you see a little bit of difference here, but it's just not that it's just not that much different. Not different enough to make it to be noticeable in real workloads. So EBS, it's like, hey, not only is NVMe SSD, kind of invisible here, but hey, EBS looks pretty good too. So one of the reasons why EBS, which is technically slower, does so well is databases themselves. We know about caches, and we build them into ClickHouse. There are a bunch of them. Here are 5 examples. So for example, we have primary key indexes on every table to help us find rows quickly. Those are in memory. In fact, they're designed to be very sparse. We have mark caches, which help us find specific blocks of data for specific rows. We cache indexes. We compress some of the uncompressed blocks, and if all that fails and we need some more caching on disk, and we have quick disk, we can build a disk cache as well. So ClickHouse is actually, even though we turn caches off, ClickHouse is doing a lot of caching for us, which makes a lot of the cost of I/O lower, because, for example, with the primary key indexes, just to take one example, we can often find stuff very quickly without having to go to disk and look for it. So it's just reducing the amount of I/O, and we don't have to even do reads to load the indexes. So when we compare the cache query response so then that says, okay, let's just look at cache queries. Another test, and compare NVMe. This is the speed champion. Everybody knows that, or all VCs know that. Versus EBS, this pokey EBS, pokey storage area network. Well, another surprise is in this test, every single EBS query was faster than every single query backed by NVMe SSD. So that's a little bit surprising. Now, remember, we're reading from the buffer cache, or the page cache. So why is that performance the same? Well, here's what I think. See, here's the 2 VMs we're testing. Does anybody notice a difference between them? Size of the VM? Well, they're actually pretty much the same VM. They have the same number of vCPUs, but that's a good... Different CPU? Clock rate. We have a winner. We have 2 winners. So yes, this is 39% faster. And that is basically a large part of the difference that we're seeing here. So even though the NVMe SSD is on the i3, should be quicker for reads, just having a faster clock speed makes your storage faster. That's I don't know if you knew that coming in, but this is something to take home and tell your friends. So that's kind of, and that's why, performance testing, that's why I say there is no truth in this stuff. There's just a bunch of, you have this journey where you dig in and you find this peculiar behavior. I had to run these tests many times to try and, sort of disentangle some of this behavior. And also, there are many, many corner cases here, particularly in the cloud, because we don't understand how this stuff works underneath. And there are edge cases that you only understand when you actually see them. Let's look at object storage. So here's how object storage is built into ClickHouse, and actually most analytic databases like Snowflake, like BigQuery, do something kind of similar. What they'll do is they'll store the data out on S3. So they'll have, they'll break the table up into pieces, compress the daylights out of them, and then push them into S3. And then when they do reads, what they're going to try to do is they're going to try and grab the data and then pull it into a disk cache. So that, and it's the reason is not just because the storage is faster when it's read cold. We already saw that S3 is pretty good. The problem is that the thing you want to do is once it's in this disk cache, we can then lean on the OS page cache and get this nice speed up almost for free. So you do that, or you can just read straight from S3. And a lot of analytic tools do that as well. So for example, if you're using Spark, it may just be reading straight off S3. So that's how, actually this says Altinity.cloud. That's how it works in Altinity.cloud, but what it really means is how it works in ClickHouse. So here's the test results for S3. Hey, that's pretty fast too. And now we do see some interesting, we see some cases where these guys are broken out a little bit, so there is some perceptible difference. Actually, this was faster than EBS on that one query number 24, which is very pokey. But it's fast, and so anything you've heard about object storage being slow is simply not true, provided you're using it correctly. What is interesting, and this is the one place where I could prove in this benchmark that S3 is slower, is it's slower on small queries. And this is an example of where we're reading directly from storage. And this yellow line, so this is a log scale, so we have to have a log scale to be able to see this. But for example, we've got queries here where there's substantial separation between the speed of ClickHouse versus the speed of S3 storage. Does anybody know why that is? Why it's slow on little queries? Any guesses? Latency. Who said latency? Okay, yes, it's latency. Time to first block, because you're having to do a hop across a network to get this stuff, and S3 is just not very quick at that. So that's where we do see a difference with setting up the call and then actually fetching the data tends to be slower on S3, unless it's working through a cache. But in this case, it's not. It's going out, finding the S3 files, and pulling them back. So the place where we see the real performance differences is actually the place where the big deviation, you can see that you have close to order of magnitude differences for some of these smaller queries. So that's, again, if you're doing a low latency data warehouse or anything that's really guaranteed low latency, you don't want to be reading from object storage. All right, so that's the research. Here's the conclusion. Well, the interesting thing that this reveals, and this is a lesson for ClickHouse, but it's also true of any good data warehouse, is they're much less sensitive to I/O speed than databases like MySQL are. And that's because they're designed to read a lot of data. So if you spend a lot of time on I/O, it's going to be slow. Here's an example. This is taken from another data set, but it's some airline data. And if I load it into MySQL, it goes in uncompressed. It was about 200 million rows. It'd be 60 gigs, which is big. I mean, that's a lot. That's a fair amount of data. And in MySQL, if you wanted to do a query on 3 columns, this particular database had over 100 columns, MySQL would read every single row just to get the data from those 3 columns. So that big sphere represents how much data you're scanning. In ClickHouse, because it's a columnar store, the data are stored, the columns are stored in separate files. We would open up the files only for those 3 columns, so we'd already reduced the data by 97%. Then on top of that, those columns might be compressed. In ClickHouse case, these 3 columns were compressed very well. So in fact, all we had to read was 21 megs of data compared to 60 gigs. We had 8 threads, and for example, if they're reading off an SSD, they're doing it in parallel, they only read 2.6 megs apiece. So as a result, in this particular query, I/O costs were a tiny fraction of the actual cost of running the query. And so what that says is that that test was just not enough data to really, to really have this stuff show in the results. And in fact, the test is really testing CPU speed. So because it's just not very big. So now, of course, and this is where performance testing can be really misleading. The tests we've done are very carefully controlled here. We're not having other applications running. We're not, sort of having a lot of concurrency. In real systems, we don't have best cases. And here's 3 examples of where these results that you just saw can be very, very misleading. So server startup. So we have cases where we know from working with customers that the server startup on NVMe SSD can be 100 times slower. And this is for people who are running in-house. They have the whole host. They have very fast storage. If you want your storage, your server to come up quickly, use NVMe SSD. Here's another one: scanning table scans of billions of rows. If you're going to EBS, going to object storage, they're just bandwidth limitations per host, and so you need to shard your data. And this is something that these performance tests don't really show. So, and that's basically the equivalent, and all data warehouses do this well. It's the equivalent of adding more spindles. And then the final thing is if you want guaranteed low latency, the simplest thing, put your data in block storage, let the OS page cache plus your database caches do their work, and that's how you get sub-second response or sub 10 milliseconds. If you come to our desk, I can show a demo that gives you an idea of how fast these responses can be. So what did we learn? Well, there's actually a number of things, and these are not necessarily closely related, but things like just NVMe SSD. People say it's fast. Well, actually not always. So another really interesting thing, and this is very basic Amazon and cloud behavior, is that VMs give bandwidth out based on their size. So we saw that with storage bandwidth. That is documented in Amazon. You can run a test that proved it, like the one that you saw a few minutes ago. Analytic databases, they work to make I/O not be very costly. Otherwise, they wouldn't be good. So you have to assume they're going to be trying to use, because these are databases that are built to run queries across a lot of data on very cheap storage. So they're going to use compression. They're going to use caches. They're going to use all kinds of tricks to skip stuff. We talked about domination of compute. And as you're thinking about building applications, I think know your caches is a really basic rule for performance. Like where are all the places where data is being hidden on the way to the CPU? The more you have of those and the more effective they are, the faster you are. We didn't see this, but know who shares what. I mean, the fact that EBS is on a dedicated network means that it will have more stable performance than object storage, where you're competing with other applications using the network. And then a couple of things like slow CPUs make your storage slow, and then object storage as slow time to first block. These are things that, and there's much more about object storage to learn. It's actually quite complex, given how simple the service looks. Optimizing performance on it has kept PhDs busy. So that's it. And the final lesson is, hey, don't trust anything I said. Do it yourself. And this code that we have, I'm going to publish this. We need something that allows us to test this for our own purposes. But yeah, trust no one and do your own tests. Here's background information, and then, yeah, thank you. Any questions?